Welcome! In a recent video from Matt Parker, he and Dr. Hannah Fry
It's actually Professor Fry.
are doing an experiment.
Where an old genius called Alberuni measured the radius of the Earth using some triangles. And I thought today we could repeat that experiment here using the shard.
Where's Steve? How can you do an experiment without Steve? Lots of things go wrong with precision. That's why I made this video. Now, for those of you who haven't watched the original video, first of all, it's funny, you should probably watch it. But just in case you don't want to, here's a quick summary of their experiment. There is the Shard, which is a tall building in London, and they are going to sit on the top of it, well, near the top. It's of course on the Earth, which is approximately a sphere, and from here they are looking at the horizon, which is perpendicular to gravity, which obviously is pointing straight to the center of the sphere. This is not the center, but you get the idea. And from here they are looking at the horizon, which is where it just touches the sphere. And so this angle they will measure, and I don't remember what they call it, but this angle they can use when they also know the height of the building, so the height from where they are measuring. They can use it to compute the radius of the Earth. That's what they're going to do.
What more can you ask for?
Precision.
Yeah, Matt is right about that. We will see. Let's see if you can do better than them. I have put several questions in this video, and I hope you will know the answer. And let's see if they do too. First of all, let's have a look at what they say about the equipment. Matt mentions it twice.
I've only marked to the nearest degree.
Sure.
And then, but you've just got to estimate what percentage through.
You're doing to a degree?
I want to the nearest 0.1 of a degree.
Oh my God.
So the question is, with a line for every degree, is it correct to measure in the nearest 0.1 of a degree? The answer is yes, that is entirely correct. So they're off to a good start. Now, let's see what they're measuring.
If I point this at the viewing deck,
Sure.
So he's pointing it at the viewing platform here and not at the top of the building. The question is that correct? Should he indeed be pointing it at the viewing platform instead of the top? And the answer, of course, as you can see here, is that yes, he should point it at the viewing platform, because that is the top of the triangle that they're going to use for determining the radius of the sphere. Now let's see, what do they measure?
what do you reckon?
22.9.
22.9. 22.9.
Does this appear to be a good measurement? Yes, it does appear to be a good measurement. Of course, we don't actually know the value that it really is, but it is to the nearest 0.1 of a degree, and that much we know is the correct precision.
Okay, I reckon that is about 20 point... Do you know, I think it's... You're wibbling around wildly between 19.5 and 20.5. So let's just go 20. 20.
Again, does this appear to be a good measurement? No, this is not a good measurement. They say it is moving around a lot, and obviously that gives you the idea that maybe if you have here, you have some lines, and let's say it is moving around between here and here. And so you might think, okay, this is the precision that I have, and well, I just don't know, it's probably somewhere here, but it's really imprecise. That's not actually the case. It is moving around a lot, but they know that the center of the moving around is actually what they're measuring. And the center can be pretty accurately determined, so it should be 20.0 and not 20. This is the reason I made this video, and that's why I'm going to give a bit more of an explanation. I've drawn a bit of a number line here from 19 to 21, and so they have a measurement of 20, or as I would say, 20.0. What's the difference between 20 and 20.0? Well, if you put it in a spreadsheet, there would be no difference. It will say the same thing. Calculator, also no difference. But when you're doing an experiment, there is a difference. And what is it? It is the precision. If I say 20, what I'm saying is, okay, this is my best guess for what actually is the value, but I'm not entirely sure, and I'm never entirely sure. The question is, how sure am I? Well, if I say 20, what I'm saying is that the last digit here, you know, it might be plus or minus 1. You could say plus minus and a half, but I don't really care. It's not that important how big it is. It's about orders of magnitude. So plus minus 1, which means that when I say 20, I really mean somewhere between 19 and 21. So somewhere in this region is where I think the actual value is, the one that I tried to measure as good as I could. But obviously the measurement is not perfect. So anywhere in this region, it is, my best guess is 20. That's what I'm saying when my measurement is just 20. When I say measurement is 20.0, what I say is, okay, 20.0. The last digit here is 0.0. That means plus or minus 0.1. So in that case, I'm saying somewhere in this region. So I'm really a lot more certain about where it should be. In this case, they are indeed a lot more certain. They can pretty accurately determine what is the center between all the bobbing around, even though it does bob around a lot apparently. Still, the center is pretty accurate, and they should have read to the nearest 0.1 of a degree, as Matt said in the beginning he wanted, but then they both agree to just say 20 instead of 20.0. And that is, well, disappointing. Finally, they need to measure the angle when they are at the top of the shard here. Now they have several problems trying to do that.
1 degree.
1.
We need decimal places on
Wait,
these
it doesn't do sub-degree.
Okay, I understand their preferred measurement devices were taken from them, but still, really, you couldn't find an app that did 0.1 of a degree? This is just embarrassing. Anyway, next problem.
Where's the horizon? Is it like...
It's a bit mountain range
Is
over
it
there, isn't
mountainy?
it? It's a bit mountainy.
Top of the mountain, bottom of the mountain? Like there's going to be a difference.
Okay, this problem is really serious, and it wouldn't really have helped to have better measurement equipment. The angle they're going to measure is apparently about 1 degree, and well, if you don't know exactly where to point, you easily have 1 degree of error in it, which means 100% error, and that is horrible. It will ruin your entire measurement, and it doesn't matter what else you did. So the result is going to be very, very wrong.
Is that wrong? I think that's wrong.
Well, I will just ignore that for now, and I will have a look at the computations. Now, they don't work it out in detail, and I won't either, but I will just show you that it can be done. We have the shard, height h, which is the one we want to find, so we don't know it. And there's a triangle here to the ground, and then to the point where they start measuring the first angle. So the angle A here is measured, so that one is known. The distance here where they start is not known. They don't know how far from the shard they are. So we have, if we use some sine function or tan or whatever, we will have an equation, and it has 2 unknowns. So one equation with 2 unknowns cannot be solved. You always need at least as many equations as you have unknowns. So because of that, they measure a second point. There they also measure the angle, and they do measure this distance, capital D, and therefore we have another triangle here. This is small d plus capital D, so that is the same unknown as in the other equation. The h is obviously also the same, and the b was measured. So we now have 2 equations with still only 2 unknowns, which means it can be solved. Now, as I said, I won't do that, but this is the answer that they also find. And what I do want to do is enter the values that they have measured into it. So capital D is 100 meters. The tan of the first angle, I write it here with the last digit here in parentheses, because that is the good way to do it. They measured it in 3 significant digits, and so I have 3 digits I know, but there is obviously a lot more when you put it in the calculator, and you should use them, or at least the first one, because the rest really doesn't matter much. But you should really use a value as good as possible, as precise as possible. So this is 10a, this is 10b, and this one here is 10a minus 10b. So you see that here you have 0.422 and we have 0.368, and if you subtract them you will get 0.058. Now the question is, we get an answer here when we put that in the calculator, and how many significant digits should we have for this answer? The correct answer, may surprise you, is 2. The reason is we have our inputs here of 3 significant digits, but when we subtract them, as you see, we only have 2 because this one becomes a 0. And so this value only has 2 significant digits, which means that the result of this division also only has 2 significant digits. So that shows you that it's actually important to measure the angles to 0.1 of a degree, which means 3 significant digits, because otherwise they would have had only 1 left, which is not very good. Now obviously we already know it won't be very good anyway, but that shouldn't be a reason to just do nothing at all. So let's see what Matt and Hannah have to say about it.
If you did that to one significant figure,
3 times 10 to the 2. Yeah, you know what? I'm picking up on what you're saying here.
And then the question is he correct? Obviously that is not right. We just found that we should have 2 significant digits, and so doing it in 1 is not correct. Now, as you can see in the video, they're not actually using this kind of analysis to determine what the correct number of significant digits should be. They are just saying, well, if you round it this much, then we will have a number that is actually close to the value we found in the brochure. Which sounds reasonable, that when you know that you're off by this much, that maybe you should correct it to use the real value that is actually the actual height of the building. However, in this case, that is not actually true. The height of the building, as they say, is all the way to the top, and so you expect your value to be a bit lower, and it is a bit lower, which means that they should have used their own value, and they should not have gone with the idea to just round it to be closer to the value they thought was correct.
Wait, is that the whole thing, or is that to the viewing platform?
to the viewing platform, so it's probably
No,
300. No, wait, so sorry, this is the whole thing.
Yeah,
The
yeah, so the viewing platform, I'm just eyeballing it. I would say that's maybe 37 meters. So.
Oh, now you're eyeballing it.
Okay, I shall agree this is definitely funny, but it's also completely inappropriate. Eyeballing it in this case is exactly what maths should be doing. The idea is they have a value from the brochure to the top, they have a measurement to here, and they don't have any other information. But they can see it, and so they can compute. If you know this total value of the building and the place from where they were measuring, or to where they were measuring in this case, then you can obviously easily find the height of this part from the viewing platform to the top. And if you look at the building, you can, by eyeballing it, you can see if it seems reasonable that this is the distance that you think it is. So doing that is actually a good way to check if your answer might be correct, and that is not something to say, oh, you're eyeballing it and it's totally inaccurate. No, it's not. This is a good way to check if what you have computed makes any sense at all. Now then, let's see what they do now.
Let's use one significant figure.
Okay, deal.
Okay.
Is that right? No, it is not right. They had just figured out that the result of their measurement was pretty good. It was actually reasonable compared to the value in the brochure. And so there's no reason to do more rounding than you need to. The result is in 2 significant figures, and so they should have used 2 significant figures. Matt actually says it best.
What more can you ask for?
Precision.
Indeed, so use 2 significant figures. But it shouldn't really matter all that much, because when you say 3 times 10 to the power of 2, or if you do it right, 2.6 times 10 to the power of 2, what you're doing is just presenting the number in a way that shows how much confidence you have in it. so how much precision there is. It shouldn't really matter much for the computation anyway. But then they do this.
So we now know and have verified that our h here is 3 times 10 to the 2 meters.
And to be absolutely clear, that is the number they are going to use in their computation. Is that right? No, of course it's not right. How do you not know this? I just do not understand how Matt and Hannah can make this mistake. This is so basic. If you have a value and you round it for presentation, you should always use the non-rounded value in your computations. The idea that you would use the 3 times 10 to the second as 300 is just, I just do not understand what they're doing. And we will see how bad it is in a moment. But first, let's find out what I have done to actually make any sense of all this. Because obviously with the angle measurement, with the huge error in it, that is a problem. And so to say anything of substance, we need to make sure there's a solution for that. What I have done is I have computed the angle that they should have measured. So based on the actual height of the platform that is given later in the video, I have used the actual radius of the Earth, and so then I know the angle that they should have measured if they would have done it really accurately somehow. So that's good. Now the question is, were they close? Well, not really, but that was obvious for the reasons already stated. The value it should have been was 0.500 degrees, which is nice and round by coincidence. So what I'm going to do is suppose that they did actually measure 0.500 and then use the other values that they measured, which obviously weren't exactly correct, but they were not that bad, and then see how that, what result they would have gotten in that case. So this angle at the top is really hard to measure, and it's therefore really impressive that the ancient Greek guy did it so accurately. Well, they didn't, and so that means that the values that they got were really wrong. But what if they would have measured this angle correctly? Well, if they would have used this computation to get the 264, and then used that in their computation for the radius, they would have gotten 6,922 kilometers, obviously in only 2 significant figures, which is pretty good. It's actually slightly less precise than what it suggests here, because the real value would have a 3 here instead of a 9. But, well, not bad, and actually it's within the range that Hannah was saying, maximum of 1,000 kilometers off. Now, what is this value? That is what you get if you do what they did. If you say we're not using 264, but we are using 300. We are rounding it for no reason whatsoever. We just add an extra 1,000 kilometers to the radius. Now we are no longer in the acceptable range according to Hannah's standard. So you have just ruined your answer for no reason whatsoever. In other words, I will say it again, never ever use rounded values in a computation. You do not round and then compute. You always use the value that you actually think is the most accurate guess of the value that you are looking for. So you might be thinking there is some truth to what Hannah had to say.
Matt and I shouldn't do scientific experiments.
No.
Is she right? No, she's not right. Science is a lot of fun and everyone should do it. You should do it too. But if you're an educational YouTuber like Matt and Hannah, then it might be a good idea to invite someone who knows a bit more about doing experiments. You know, like Steve. Maybe Steve doesn't want to talk to you anymore after that video you did with him. You might have considered treating him better. Anyway, that's it for my response to their video. There's 2 main takeaways that I want to repeat here. First one, which is what I just mentioned. Everyone should do science. It's a lot of fun and you should enjoy it. And second one, never ever use rounded values when you are doing a computation. You can round them, you should round them for presentation, but that's it. If you're doing a new computation, you use the non-rounded value. That's it. I will see you in the next video. Thank you for watching.